All right, so the first thing you want to do is draw your free body diagram of the problem. So we'll do that right here. So due to the symmetry of the problem, there's a couple things that you can figure out right off the bat. So for one, we know that because it's a fixed support at both ends, that there's going to be some reactions involved. Let's call this point A, point B. So we're going to have an X, a Y, and then a moment at both ends. So we'll have a VX, an AX, an AY, an MA, BY, and MB. But because the bar itself is symmetrical and everything is symmetrical in this problem, there's a few things we can say. For one, the vertical reactions at both ends would be equal to WL over 2. Now, why is that? Well, if you were to convert this distributed load right here into a point load, it would look something like this. It would act halfway between the bar and the fixed end, and it would have a magnitude of WL. And because it acts halfway, that means that the two reactions have to be equal and opposite from one another. And on top of that, it's divided by 2 so that the whole bar itself is in equilibrium. So once you have that kind of determined, you next do a cut, a section cut. And we'll do a section cut about this end right here. Something like that. So we'll label that cut 1. So just do this. So cut 1. So if we draw a free body diagram of that cut, it would look something like this. There's a shear at the end and a moment. We have our AY, but we figured out that AY has a value, which was WL over 2. So instead of writing AY, we should write WL over 2. We also have, technically we also have AX, and We also have an MA. And then we have the distributed load right here at the top. The magnitude of W. And that cut that we're making is at some arbitrary distance. So we could just label that X. So in order to continue doing the problem, let's sum moments about C. So if we do that, we do some moments about C, about the cut. So we would have in this expression M, same M that was created by the cut, plus the moment that is created by the distributed load. So again, in order to do that, you want to turn your distributed load into a point load. And when you do that, it would have, in this case, a magnitude of Wx, and it would act halfway between the cut and the force. So it would be plus Wx, the magnitude of force, times the distance at which it acts upon, which is x over 2. Okay? Plus MA, we also have MA right here, the moment caused at A by the fixed support, minus WL over 2 times the distance from C, which is x. And all of that equals to 0. So now we want to solve for M. So if we do that, M would be, in this case, it would be WL over 2 times x minus W over 2 x squared minus MA. So now that we have an expression for M, for the internal moment of the beam, we can use the following equation to solve the problem. So if we plug in for M, we would have this. So we integrate once, and we will get EI dy over dx is equal to WL over 4 x squared minus W over 6 x cubed minus MAX plus C1. And then you integrate one more time, and you get EI of x is equal to WL over 12 x cubed minus W over 24 x to the 4 minus MA over 2 x squared plus C1 x plus C2. So this is what it should look like once you integrated it twice. Now that you have that, you want to establish your boundary conditions. So let's look back at the problem and establish those. So we have a fixed support at both ends. So we have a couple of boundary conditions that we can say. First of all, at x equals 0, the displacement of the bar, or y, will also be 0. And the same thing goes for x when x equals L. Y is going to be equal to 0. So similarly, because to also fix support, the deflection at those ends are going to be 0 as well. Or not the deflection, the slope, I'm sorry. So at x equals 0, dy dx is going to be 0. And at x equals L, dy dx is also 0. So you have 4 boundary conditions that you could work with in this problem. And I'm going to go through which ones would be easier to do. Apply boundary conditions. So for the most part, the boundary conditions that you want to prioritize and use are the ones where both of the things are equal to 0. So this one's pretty good. X equals 0, y equals 0. And this one's also pretty good. X equals 0, dy dx equals 0. And you're going to see why I chose these ones first. So if we substitute in these boundary conditions to solve for our constants, let's do number 3 first. So if we apply boundary condition number 3, x equals 0, or y dy dx equals 0. So that left side is going to be equal to 0. Right here. And if we plug in 0 for all these x's, 0 plus 0 plus 0 plus c1. We're just going to find out that c1 is equal to 0. That's pretty good. Next, let's apply boundary condition number 1. So again, it's kind of the same process here. You plug in 0 for y, and you plug in 0 for all your x's. And when you do that, you're just going to get a lot of zeros. 0 plus 0 plus 0 plus 0 plus c2. So you end up finding out that c2 is also equal to 0. And that's why I chose these 2 boundary conditions over the other 2. Because if you choose boundary conditions where both of the things are equal to 0, then everything tends to just cancel out and equal to 0 in the end. So it makes your life a bit easier. So solve for constants. So we already did that. We already solved for constants. So that means that this expression that we found for the deflection ends up simplifying down to this right here. Okay. So what else can we do here? Well, let me make another page. We still have one more boundary condition. Actually, no, hold on. We still have the other 2 boundary conditions that we didn't use. So let's use those. In this case, the only one that we can really apply is the second one, right here. Because this expression that we have is y of x. And it's the only boundary condition that we have left that can apply. So if we plug in what we already know, that is y of x equals 0 at x equals L, we'll get the following. W over 24, L over 4 minus M A over 2M squared. Okay. Now that you have this expression, you can solve for MA. So if you do that, you get MA over 2L squared is equal to WL to the 4 over 12 minus WL to the 4 over 24. Right, let's just move this over to the left side. And then multiply these two together. And finally, if you do a little bit of simplifying here, we can simplify this a little bit. So these L squared cancels out, and these convert to L squared right here. And then if you were to do this subtraction right here, it would be equal to WL squared over 24. Let me just double check. 2, yeah. So yeah, you'll have this expression right here, and you just solve for MA, which will be WL squared over 12. Whoa. Let me just double check that that was the answer that I ended up getting, and yeah, cool. So now you can just organize everything because the question itself asks to solve for the reactions at A. So your reactions at A, you had an AX, you had an AY, and you had an MA. Your AX is technically just equal to BX. AY, you found to be WL over 2, way back all the way over here, because of the symmetry of the problem. WL over 2. And MA, we just went through that whole process of solving for it, which was that. WL squared over 12. So yeah, those are your reactions at A. Now the last thing that the problem asks is draw the bending moment diagram for the beam and loading shown. Okay. So let's do that very quickly. So first of all, the shear diagram would look something like this. Oops. It would look something like that. It would go up by a magnitude of WL over 2. And then because it's a distributed load at the top, the shear would look like a triangle. And then it will jump back up with the magnitude of WL over 2. So that's your shear. It's very quick, very conceptual. The moments diagram should look something like this. So there is a fixed end at both ends. So you're going to start off with some moment. So double check something real quick. Okay, well, let me just copy this real quick. So the moment diagram is associated with this expression that we came up with earlier. And so you technically want to be plotting this curve into the moment diagram. Now it looks a bit tricky, but there's a few things that we can make our life a little bit easier. So for one, if we start at x equals 0, these two terms would cancel out. So you find out that the moment at x equals 0, the internal moment at x equals 0 equals to negative ma. Now we already found out that ma is wl squared over 12. So that means that in the moment diagram, we will be starting at negative wl squared over 12. We would be starting at the bottom just because of what this expression is telling us. Similarly, if we look at x equals L, x equals L, we plug in L where we see x. We also see that those two terms would end up canceling out. These two terms cancel out. So again, you get that m equals negative ma at x equals L. So it'd be something like that. Lastly, because this shear diagram is as a linear line, that means that our moment has to be in the shape of a parabola. And that's kind of justified with the expression that we found here. So you just kind of connect the two dots together in the shape of a parabola. Oops. Let's do that again. And yeah, that's kind of how your moment diagram should look like. And that's pretty much it.